So let's continue our discussion on ring theory. Okay. So in the last lecture we have discussed a bunch of things. Okay. And in this lecture we're gonna start the discussion. So I'll start the discussion by first somewhat proving the division algorithm, or rather the what we call the division of polynomials. Okay. Because in the last lecture proving the division algorithm for polynomials. Because in the last lecture, if you recall, we had given an essential discussion on what the degree of a polynomial is, so on and so forth, and some things which you can immediately observe. So yeah, so let us start the discussion. Okay. So some things which you can immediately observe is that suppose R is an Euclidean domain. Sorry, R is an integral domain. Okay. Suppose R is an integral domain or a domain. Then in the previous lecture we had proven that Rx will also be an integral domain or as a domain, right? Simply a domain. Right. So if I choose two elements f and g from Rx, and then I multiply them out and I try to find the degree of these polynomials. I mean, I am multiplying two polynomials over Rx and I'm trying to find the degree of it. Then you can obviously observe that the degree will be degree of f plus the degree of g, right? Because the degree is completely determined by the leading term of each of these polynomials, right? This is something which we know already. So, and we also know that if an is the leading term of f, then that is non-zero. If bm is the leading term of g, then that is also non-zero. Since it is a domain, therefore a and bm can never be zero. And if it is non-zero, then this is the highest coefficient of the leading term of the product of polynomials f and g, and they correspond to x to the power n plus n. Where n is the degree of f and n is the degree of g. Right? So I hope you are getting my point. Right. So as I said, what we are intended to do firstly is to prove a certain factorization of polynomials. Okay. So you can take this to be a theorem. So it is what we call the division algorithm. The division algorithm of fx. Okay, where f is a field. And if f is not a field, we will give the necessary criteria for the division algorithm to hold. That is not a problem. Okay. So what the statement says is that if if f is a field and let f and g come from fx, sorry, such that g is not identically zero. That is, g of x is non-zero for every element x. That is something which we have. Then there exists polynomials qx and rx in fx. Basically, they are uniquely determined in this case because we are talking in a field. We will say why the uniqueness comes specifically for a field. Okay, so it's uniquely determined such that I can write f of x as g of x times q of x plus r of x, such that either r is identically 0 or the degree of r should be less than the degree of g. Clear? Okay, fine. So you can somewhat relate it to the usual division in integers, right? And this is somewhat, the proof is somewhat the same. Okay, let's try and prove this. We have never proved it like right. No. Whenever we need to resort to a proof of the division algorithm, whatever we stated is that it is simply the long division method, right? That is, we start with g and we keep dividing as we divide polynomials, and we will essentially get such structures. Okay, here we are going to go resort to a rigorous proof. Okay, so the proof. Okay, so suppose f of x is 0. Okay, or let's say the degree of f is less than the degree of g. That is, we are dividing f with a polynomial of higher degree. Okay, then what we can do? Then we can set q of x to be the 0 polynomial, and I can set rx to be f of x. Okay, then you can just relate the facts and you will see that r satisfies the condition required, and in fact the division is satisfied. Okay, therefore let f of x be non-zero. Okay, or rather f is not identically 0. That is what we mean. That is, I mean, it is non-zero for all x in some sense, like that. Okay, or what we specifically mean, certain symbols carry different meanings. There might be some elements in f such that f is 0, right, which are called the roots of f. So that shouldn't resort to the correct notation. This will be a correct notation. F is not identically 0. That is, f is not the 0 polynomial in some sense. Okay. So what we are going to do? So we have already encountered two cases, that either the degree is less than g or f is identically 0. So, and the degree of f is greater than the degree of g. That is what we are going to count. Okay. So just for simplicity, let the degree of f be n and the degree of g be m. Okay. So in that case, I can resort to a notation. So let fx be a0 plus a1x and so on and so forth till a n x to the power n. I can write gx to be b0 plus b1x and so on and so forth till bm x to the power n. Right? I can do this. Fine. Now what we do is that let f1 of x be f of x minus an bm inverse x to the power n minus m gx. Okay? Clear? Now observe the thing. What can we say about f1x? Therefore, either f1x is identically 0, that is the 0 polynomial, or the degree of f1 is less than the degree of g. Sorry, degree of f. Degree of f1 is less than the degree of f. Okay? Now see, what we are on the background, what we are doing is that we are basically inducting on the degree of f. Okay? Now if f is a degree 1 polynomial, okay, if f is a degree 1 polynomial, then what we know is that then f must be a constant polynomial, right? If it must be a linear polynomial, right? But if it is a linear polynomial, then factorizing it makes no sense. What I mean by makes no sense is that it's a very trivial check. Okay, if the degree of f is 1, then it's a very trivial check to find q and g, q and r, or rather given g, q and r, right? Because since we are assuming that the degree of f is greater than or equal to, we can also consider the case equal to, no problem. But then there is actually nothing to do. If the degree of f and g are the same, then you will get q and r to be constant polynomials, right? You can just check it arbitrarily. It makes no problem in checking that. And what we can further assume is that the given hypothesis holds for all polynomials. So the given hypothesis holds for all polynomials f1 such that the degree of f1 is less than the degree of f. So this is our induction hypothesis. Okay, you should already get a hint that we are using the second principle of mathematical induction, right? Yeah. So once we get hold of a polynomial which satisfies the induction, so f1 must satisfy the induction hypothesis, right? Therefore, let me change back to blue color. Therefore, by induction hypothesis, what we can resort to is a factorization of f1. So I can write f1x as gx times some q1x plus r1x, okay, such that r1 must be 0 or the degree of r1 is strictly less than the degree of g, right? No problem in that. But once we have this, what can I say about fx now, right? So therefore, my fx can be written as an bm inverse x to the power n minus m gx plus q1x into gx plus r1 of x, right? So this can be written as an bm inverse x to the power n minus m plus q1 of x, this whole times g of x plus r1 of x. Clear? So therefore, if I assume this to be q of x and I take this to be r of x, we are done. We are done. Got my point? Right? Clear? Now, we are also given the notion of uniqueness, but the uniqueness is pretty easy, right? Because observe that if I can write fx as say gx times qx plus rx, where all the necessary conditions hold, and also as gx times q bar x plus r bar x, then this implies that gx times qx minus q bar x plus rx times r bar x, this must be exactly equal to 0, right? Fine. So what do we conclude from here? So from here we conclude that rx minus r bar x, right, or rather sorry, r bar x minus rx, okay, wait, minus rx, this should be equal to gx times qx minus q bar x, right? This is something which we can get. Therefore, from here what we conclude is that therefore either r bar x minus rx is 0 or the degree of r bar x minus rx, this should be at least the degree of gx, right? Right? But when is this possible? This is possible if the degree of r bar x or rx is greater than the degree of gx, right? Fine, greater than or equal to in some sense. Yeah. So this is clearly impossible, right? This is not possible. Therefore, r bar x minus rx must be 0. So they must be equal to each other. And if it is 0, then I have gx times qx minus q bar x is equal to 0. Since f is a field, f is an integral domain. So if x is an integral domain, so this is an integral. This is the multiplication inside an integral domain. We know g is assumed to be non-zero. Therefore, this must be 0. So q of x must be equals to q bar of h. Right? Yeah. Fine. So thus we prove the uniqueness. Here we have proven the uniqueness. Yeah. So there are two things which you should carefully observe here, that the uniqueness or rather the existence of this division algorithm, it solely depended on the Bm inverse to exist, right, and integral domain condition, right. These two are required for the division algorithm to exist and the uniqueness to hold as well. Yeah. Therefore, if I remove the condition of f being a field, so suppose f is not a field, f is not a field, so I replace f by some r, which is a commutative ring with unity in accordance with whatever we were discussing in the previous lecture. What can we conclude is that the only condition for this division algorithm to exist is that the leading coefficient of gx is a unit, right? Because we only require the inverse of bm, the leading coefficient of g. Fine. Also, we can easily observe that the uniqueness, for uniqueness to hold, what we require is the notion of an integral domain. So we require R is an integral domain. Now you can easily observe that if Rx is an integral domain, R will automatically be an integral domain, right? Because I can consider the constant polynomials in Rx; those are exactly in correspondence with the elements in R. So obviously, two non-zero constant polynomials being multiplied to 0 will imply that one of them is 0, because the Rx is an integral domain. That automatically implies R is an integral domain. So it's an if and only if condition, which you can clearly observe. Getting my point? So for the uniqueness to hold, we require R to be an integral domain. Fine. Therefore, the same statement, let me just go back to the statement where I wrote the statement. So the same statement will hold exactly if I consider a ring R a commutative ring with unity, such that Bm, which is the leading coefficient of G, is a unit. Okay. This gives me the existence of the division algorithm. Fine. This gives me the okay. Now you can easily observe it that Bm, if the inverse of Bm exists, or if Bm is a unit, then we get hold of everything we require for the division algorithm to exist. I mean the division to exist. Okay. And for the uniqueness, what we require, that R is a domain. Right. So the same statement will hold except uniqueness if R is simply a commutative ring with unity, if the leading coefficient of G is a unit. Okay. And what more we can conclude is that if R is a domain, then the uniqueness will hold in addition. Got my point? So in fact, what we can say from here is that, so in Z4, the factorization might not be unique because it's not an integral domain. Yeah. Okay, fine. Now let's come to, so what we have proved is that the division algorithm holds in polynomials over a field, and it's unique if the field, if I simply replace or a commutative ring with unity, whose in which case the quotient polynomial has a unit in its leading coefficient, and furthermore if the ring itself is a domain, then the division is unique, right? Once you will study unique factorization domain, you will get the essence of why this uniqueness is required. Okay. Now let us resort to talking about homomorphisms and ideals. Okay. So this the definition of homomorphism is exactly what we did in case of groups, and in case of groups we required the distributive nature in terms of the operation of the group. Here we will be also requiring that, but here we have two operations, so we have distribution in terms of both the operations. Okay. So let R and S be rings, then phi from R to S is a ring homomorphism. I won't write the term ring anymore because we are already studying ring theory. It's a ring homomorphism if point number one, that phi of Rs or rather phi of R1 R2 is equals to phi of R1 times phi of R2 for every R1 R2 coming from R. Number two is that phi of R1 plus R2 is equals to phi of R1 plus phi of R2 for every R1 R2 coming from R. And since we have the unity, we define phi of 1 to be 1. Yeah. Okay. So we say that phi is an isomorphism if phi is a homomorphism. So you can just recall how we defined isomorphism in groups. So if phi is a homomorphism and bijective. Clear? Got it? Okay. Let us consider an example. See, we had previously claimed that R is, or rather, I think we hadn't discussed this previously. Let me just discuss it now. Okay. So we had a ring R and in accordance to it, we had constructed the ring of polynomials Rx, right? And I have constantly been stating that if I have a polynomial fx equals to some r, okay, so this is the constant polynomial. This is the constant polynomial. Then this can be identified with an element in R itself, right? Or this is exactly in correspondence with the element in R itself, okay? But obviously, if you observe carefully, the way we had introduced the notion of polynomials, it was in terms of coordinates. If you recall, infinite sequence of coordinates, right? So these constant polynomials are, they correspond to the elements of the form r00 and so on, right? And an element, if you choose out of the ring, it will simply correspond to r, right? So as element wise, they do not look the same, right? But their behavioral properties are the same, okay? So as in group isomorphisms, we know that isomorphisms, what they do, they basically preserve every single properties of the groups which are isomorphic. Here we will be also having the same thing. Two rings are isomorphic. Obviously, if there exists an isomorphism between them, which implies that both of them are having the same ring structure. The structure is preserved. Okay. So, in order to rigorously claim that R is actually sitting inside Rx, a more technical term would be embedded inside Rx. What do we have is that I can simply consider a map from R to Rx by taking the element R and I map it to the coordinate this. Okay, then you can observe that phi is injective homomorphism. Okay, and whenever you have an injective homomorphism, the embedding occurs. That's exactly the definition of embedding itself. Okay, so if phi from R to S is an injective homomorphism, then R is said to be embedded in S. That is basically that R can be identified as a subgroup of S. It can be identified as a subgroup of S. In other words, there exists some subgroup, in this case a ring. So there is some subring of S which is isomorphic to R. And that subring is exactly the image of R under this map. Okay. When we will be studying the first isomorphism theorem, it will be made more clear. Getting my point? Okay. Fine. A similar example which we had discussed in the previous lecture. If we choose the map phi from R to FR, the fraction field of R, then I can take R and I map it to this element. So this will give me an isomorphism, not an isomorphism, an injective homomorphism. An injective homomorphism, which means that R is embedded inside FR. Clear? Okay. Now we have two important definitions. Given phi from R to S, a homomorphism, then we define the kernel of phi as the collection of all those elements in R which gets mapped to the zero element of S. Okay, and we define R of phi as the or sometimes is referred to as the image of phi or the range of phi to be the collection of all the elements of the form phi R such that R comes from capital R. Yeah. Okay. Now something which you can immediately observe is that lemma that phi is injective if and only if the kernel of phi is consisting of only the zero element. How can I do that? See, this is a pretty easy observation. See, so suppose kernel of phi is I am doing one of the steps. Okay, suppose kernel of phi is only the zero element. Then this implies, okay, so let me hold it to be true. Let phi of R1 minus phi of R equal to phi of R2. Then this would imply phi of R1 minus phi of R2 is 0. This would imply phi of R1 minus R2 is 0. But then by definition, R1 minus R2 must be an element of the kernel of phi. But this by definition, since kernel of phi consists of only the zero element, so R1 must be equals to R2. And the converse will hold along the same set of steps. Okay, just try and do it on your own. It's not a problem. See, the kernel will be 0 if it's injective in the following way. If you choose phi of R, or rather you can do it in this way. Let R be an element of kernel of phi. Then this would imply that phi of R is 0. But you can prove it that phi of 0 is 0. Okay, you can. This is a very easy check. Okay, but then by injectivity R must be 0. Right? Very easy proof. In fact, it's surjective if the image of phi is same as the codomain. Sorry, surjective. I say surjective, right? It's surjective if and only if the image of phi is the same as the codomain, and that's a pretty easy check. There's nothing. This is just a check in terms of functions. This just means that every element will have a preimage, right? Okay. What you can furthermore check is the kernel of a ring homomorphism is a subring of the domain ring, and the image of phi is a subring of S. A very easy check. Just go by the definition. This will help you to be accustomed with the definition of subrings. Okay. Fine. Okay. Fine. Now let us discuss some important properties, or rather a very important concept of ring theory, which is the existence of ideals. Okay, as the name suggests, these are ideal subrings, or rather most important subrings in some sense, most important subrings. Now if you go back to group theory, there also we have the notion of subgroups, but there was a particularly important class of subgroups which we used to call the normal subgroups, right? Because these were important because this helped us in constructing a new group, which is the quotient group, if you recall, right? G model. And we will see, so there we had a complete motivation of how these normal subgroups actually help us in constructing out the quotient group. And the notion of ideals is somewhat motivated from the definition of normal subgroups itself. So these are basically some ideal subrings, the subrings which carry some very important properties which help us in many of the cases of rings. Okay. So what is the definition of an ideal? So I, a subring of R, is called an ideal. Okay. So let me start by not calling it to be a subring. Let me do it in this way. So I, a subset of R, is called an ideal if, number one, that A and B are in I implies A minus B is in I. So you can observe that this satisfies the condition of it being a subring, or at least additively close. Yeah, it immediately does not give it to be a subring structure. It gives it to be a subgroup structure, a subgroup of the additive group induced by the ring. And for every R in capital R, for every A in I, R A, A R, both of these elements are in capital I. Okay, fine. Now, if you are not given a commutative ring, then you cannot see. In this case, since we are talking about commutative rings, I can simply state that Ra is in I, because it will automatically imply that Ar is in I. But if you are not given a commutative ring, then if you satisfy the condition, and condition 2 states that Ra is in I for every element R in capital R and every element A in I, this would make I a left ideal. This would make I a left ideal. And simply if you have the condition Ar is in I, this would make I a right ideal. So there both of these notions differ. Okay, there both of these notions differ. Fine. For example, we have a very important class of examples. Let me go back. Okay, let me consider a new page and let us consider the following example. Wait a second. Yeah. Yeah. So where are we? Fine. Yeah. So consider the following example. That if, for example, say consider the set X in R such that Ax equal to 0. A is some fixed element. A in R is some fixed element, and consider the set X in R such that Xa is equal to 0. Okay. Then you can observe that this forms a right ideal. Okay. This forms a left ideal. It's closed under the multiplication from the left by the elements in the ring, and this is closed by multiplication by elements from the right by the elements of the ring. This set is called the collection of right annihilators. Right annihilators of E. And this is called the left annihilators of it. In many competitive exams, you will get this question that, give an example of a left ideal which is not a right ideal, a right ideal which is not a left ideal. So they do not coexist. What I mean to say is that these are not left ideals, while these are not right ideals. Okay, keep this in mind. So when do we say that an ideal is a proper ideal? If it is not exactly equal to R. So if I is not equal to R, I is an ideal. So this is the notation we will use for ideals. This was what we use for subrings. Okay, they are basically stronger subrings in some sense. So I in R is said to be a proper ideal if I is not equal to R. And you can observe that I is basically a subring, right? Because if it is closed under multiplication by every element of the ring, it is closed by multiplication by every element of the ideal itself. It is already having the group structure, the additive group structure. So it evidently forms a subring. You can easily conclude that all ideals are subring, while the converse need not be true. Okay, the converse need not hold to be true. Okay, fine. Okay. Example. Fine. Let phi from R to S be a ring homomorphism. Okay. Then be a ring homomorphism such that phi is non-zero. That phi is not identically a zero map. Okay. Then the kernel of this is a proper ideal. So this is by notation the proper ideal of R. Okay. How can we prove this? The proof is quite easy, because see, let A and B come from the kernel. First, the kernel can never be, this can never be equal to R, as if so, then that would mean that phi of R is 0 for every element in R. This would imply that phi is the zero map, which is given not to be true by the hypothesis. So if A and B are elements from the kernel, this implies that phi of A is 0 phi of b is 0, but this implies that phi of a minus b, which is equals to phi of a minus phi of b, this is in fact 0. So this means that a minus b is in the kernel. Moreover, if R is an element from capital R, then phi of Ra is phi of R into phi of A, but phi of A is 0. So this is phi of R into 0, so it's 0, which implies that Ra is in the kernel of phi. And we can also check from the right, but we don't need because we are inside commutative rings. Getting my point? So this is the notion of ideals. Fine? Okay. Okay. Now let us continue our discussion. So this is the notion of ideals basically, and we will see that these ideals will help us construct the notion of quotient rings analogous to quotient groups. Okay, fine. Now this is very important observation. This is again a very important observation that if phi from R to S is an isomorphism, then phi inverse from S to R is also an isomorphism. So there is a sub-statement, that is if phi and psi are isomorphisms, or rather in fact simply they are homomorphisms, then their composition is also a homomorphism. From R to S is a homomorphism. Okay, no, it shouldn't be from R to S. Sorry, let me write it in a different way. Sorry, I just miscalculated the domains and the codomains. So let phi from R to S and psi, let's say from S to T, be a homomorphism. Then phi, let's say psi composed with phi, so the domain will be R and the codomain will be T. This is a homomorphism. Yeah. Whenever you are composing two functions, you should make sure that what the domain and the codomains will be. Okay, I mismapped it. Sorry. Fine. Getting my point? So how can you prove this? See, once phi is bijective, phi inverse is automatically bijective. It is automatically bijective, right? Fine. So only thing which we need to check is that whether phi inverse is linear or not. Okay. Let's see. So what we need to prove is that phi inverse of alpha A, what we need to prove is that phi inverse of A plus B is equals to phi inverse of A plus phi inverse of B, and to show that phi inverse of AB is equals to phi inverse of A times phi inverse of B. Okay, let us do something. Let phi inverse of AB X, phi inverse of BB Y. See, phi inverse of 1 is 1 is trivial, right? Because phi of 1 is 1. Right. So this implies that by definition phi of X should be A and phi of Y should be B. This implies that phi of X plus Y, if I just add these two up, should be A plus B. Or X plus Y should be phi inverse of A plus B. But X was phi inverse of A. So this implies that phi inverse of A plus phi inverse of B is equals to phi inverse of A plus B. And in the same way, if you multiply these two out, you will get XY is equals to phi inverse of AB, while XY was phi inverse of A times phi inverse of B. So this is phi inverse of AB. Yeah. Got it? Okay, fine. Let's continue. Okay. Something which we can again observe is that if phi is a ring homomorphism, then R in capital R, phi is from R to R, okay, R to S. Then R in R is a unit, implies phi of R is a unit. Obviously in S. How can I prove this? A very easy proof. If R is a unit, what do we conclude? That there exists some non-zero element S in R such that Rs is equals to 1. But then this implies that phi Rs is equals to phi of 1, which is 1. But this implies that phi of R times phi of S equal to 1. Phi of S is evidently an element of S. Therefore, phi of R is a unit. In fact, you can also prove the converse once phi is a ring isomorphism. Okay, if phi is a ring isomorphism, then the units of R and the units of S are in correspondence. You can check it on your own. There's nothing difficult to observe. Okay. Fine. Okay. Okay. Now what more should we be talking about at this point? Yeah, let me give a very simple definition which we'll be making use later. Okay. If A is in R, then the set RA such that R comes from capital R is called the ideal generated by A. Okay. or typically it is called the principal ideal generated by A. Okay, and denoted as this. Okay, this is a very easy exercise to check that this is indeed an ideal. It can clearly be seen to be closed by multiplication by elements of R. One thing to again keep in mind, I'm just giving you insight that whether there is some situation where commutativity does not hold. Observe that if R is not commutative, then this simply forms a left ideal. Again, right? Because if you multiply anything from the left, say R1, then R1 times R times A is same as R1 R times A. So it will still be an element of the set because R1 R it will be an element of the ring. Fine. So you can also define the set to be the collection of all elements A R such that R comes from capital R. This will form a right ideal if the commutativity is not given. Got it? Fine. See, when you are discussing about rings in general, then obviously the commutativity is not something which you essentially require to discuss every time. Okay. What we have done is that we have designed it or structured it in such a way that it makes studying easier by considering it to be commutative, nothing else. Okay. Fine. Got my point? Okay. So this is called to be the principal ideal generated by A, and a similar definition is that if A if A is some subset of R, then we define the ideal generated by A as the collection of all elements, finite sums, R1, Ri, Ai, I is equals to 1 to n, such that Ri comes from capital R, Ai comes from capital A. Right? So if it's a finite set, if A is a finite set, then you can also abide by the same definition, right? There the set will vary only in terms of the elements of R, and in any case this also forms an ideal. So this is called the ideal generated by the set A. Okay, we use the term principal ideal if the ideal generated is done by a single element. Okay, fine. Okay, the next observation is again very important. Observation is that if I is an ideal of R, or let me write it in this way, let R be a ring and I be an ideal of R, then I is exactly equal to R if and only if 1 is in I. Okay, or it can in fact be weakened. Let me do it in this way. Okay, we will prove in fact that it holds due to the existence of 1. So a bit stronger statement should be, or general statement should be, if and only if I contains a unit. I contains a unit of R. Okay, that is I contains some element U which is a unit in R. Okay, so let's prove this. The proof is again very simple. Proof. Suppose see, if I is equal to R, then it's trivial, right? Right? Because every element in R should be in I. So if there exists a unit in R, then it should be in I. There's nothing to prove here. We need to prove the converse. Conversely, let U be in I such that U is a unit in R. Right? So that implies there exists some element V in R, non-zero element V in R, such that UV is equals to 1. Therefore, 1 is in I. Right? Since I is closed under multiplication by elements of R. Under multiplication by R. Right? V is an element of R and UV is 1. So UV must be in I because I is an ideal. So 1 must be in I. Now observe, now this implies that R times 1 is in I, or rather this is equals to R is in I for every element in R. Right? This implies that R itself is a subset of I. But by definition of an ideal, the ideal must be the subset of R. So we have a both-sided inclusion, that means I must be equals to R. So what is the important step here? That if 1 is in I, then I must be equal to R. That was the statement which I wrote previously. Getting my point? Okay. Fine. Now this immediately gives us a very important observation. If F is a field, then, or rather, let's say it in this way, observation, F is a field if and only if the only ideals of F are the zero ideal and the whole field itself. Okay, so the proof is again very easy to observe, right? See that let's say I be an ideal. Okay, I be an ideal of F. Okay, such that I is non-zero. So this implies that there exists some element A in I such that A is a non-zero element. But by definition of a field, we know that every non-zero element is a unit. But this implies that A is a unit, which implies I contains a unit, which implies I must be equals to A. Fine. try and prove the converse. This is again an exercise. Try and prove the converse. Okay. So what we need to do is that we need to assume that that the only ideals are these, and to prove that f is a field in that case. Okay. How can I actually do it? Let me just give you a hint. Um, you can do it in this way, that suppose f is not a field. Okay. Suppose f is not a field, then there exists some non-unit element, right? Some non-zero x, such that x is not a unit. So then you can consider the ideal generated by x. It will be a proper ideal. Okay. So I actually gave the proof. Just write it rigorously. If f is not a field, so then you can take the contrapositive. By contrapositive, it will be the only ideals are 0 and f implies that f is a field. Okay. This is a very easy check. So you need to keep these things in mind, right? What are the things which we are working with, and what are the properties, what are the intrinsic properties they carry? Okay. So if it is a field, if we assume that if it is not a field, then there obviously exists a non-unit element, because if every non-zero element would have been a unit, then it would have been a field. So there exists a non-unit element, a non-zero non-unit element. Take that element, generate an ideal. We are already given the definition of a principal ideal. That will be a proper ideal. Why? Because x is not a unit. So any scalar multiple, or rather any r multiple of x will be a non-unit. Clearly, right? Because you can observe that AB is a unit, even only if both are units. Because x, what should be the inverse by definition? B inverse A inverse. So both must be a unit, right? So if x is not a unit, any Rx won't be a unit. So it won't be equal to R at any rate. Getting my point? Okay, fine. Let us prove the next thing. It's also a very important observation. All of these will come to us when we will be talking about some special domains. That is, so this is very important, that the ideal generated by the element x and 2 is not a principal ideal. Is not a principal ideal in Zx. Okay. So let me give a brief hint here. If R is an integral domain such that every ideal in R is a principal ideal, then we say that R is a principal ideal domain. R is a PID, a principal ideal domain. So this statement, what actually it proves is that Zx is not a PID, right? So we will check the proof of this now. Yeah. So fine. So we need to prove this, right? Okay. Proof. Okay. First, let us analyze what does the set actually looks like. So this looks like, since here in Zx, so this looks like elements of the form x times px plus 2 times some qx, such that px and qx are in Zx. No problem with that. Something which you can immediately observe is that if you choose any element of this form, then what should be the constant term of this element? It should be of the form 2 times q0, where q0 is the constant term of qx. It might be 0, it might be null, that is not a matter of fact. So what it actually implies is that that any element which is here, 2 must divide the constant term of it, right? So in some sense, it is actually the correction of our polynomials of the form q0 plus something, such that 2 divides q0, even constant terms. So it immediately implies the fact that this actually cannot be the whole of Zx, right? Because obviously, if I choose this polynomial 1 plus x, then it cannot be x2, the ideal generated by x2, because the constant term is an odd term, right? So this is something which we can easily conclude. Now we need to prove that it's not a principal idea. Okay. So in any case where we do not get an idea to talk about things, or rather in any case where we are asked to prove something, our first instinct should be to talk about whether, if it happens, if it would have happened that it is a principal ideal, would there arise any mathematical contradiction, right? So let there exists some px in Zx. Px is obviously a non-zero polynomial, right? Once again, yeah, sorry, some some YouTube video started on the background, right? So px is contained in Zx. Fine. So what can I do from here is the following. Okay, I often do pause the lectures and then restart, and do the fact because these are not very note-based lectures. Okay, these are just thoughts which are coming in my mind. There's a very important statement I don't actually recall who said this. I guess it was said by Poincare that you need to talk like a student or think like a student when you are teaching or lecturing on something. That is the exact thing which I try to do. Okay, I just come up with things when I'm talking in these lectures. Okay, so please pardon if there is some sort of a disturbance. I'm extremely sorry, but I try to make it as conceptual and as informative as possible. Okay, yeah. So suppose there exists some px such that the ideal generated by px is exactly equal to the ideal generated by x and 2. Fine. Now observe now, 2 should be obviously an element of Zx. An element of x, the ideal generated by x and 2. Right. This implies there exists some qx in Zx such that px times qx must be equals to 2. Right. On the right hand side, we have a, so this is a 0-degree polynomial, right? This is a 0-degree polynomial. On the left hand side, we have the product of two polynomials. Z is an integral domain. Therefore, Zx is an integral domain, right? So what can we conclude from here is that therefore, the degree of Px times Qx should be equal to the degree of the polynomial 2, which is 0. But degree of Px times Qx is degree of Px plus degree of Qx, because it's an integral domain. So it must be 0, right? But what does this imply? So this implies that the degree of both of them should be 0, because the degree is obviously non-negative. By definition itself, it should be 0, right? Therefore, this polynomial Px is a 0-degree polynomial. Hence, it is some form of P, right, which is in Zx. Or in fact, this is actually an element of Z. It's just an integer. Okay, fine. So what we conclude immediately that that P is an integer. Okay. Moreover, P divides 2, right? Because the degree of Q is also 0, so Q is also an integer, right? So this implies that PQ is equals to 2, right? That implies that P divides 2. So now we can restrict our calculation completely to integers. 2 is a prime number. That means P can either be plus or minus 1 or plus or minus 2, right? But immediately observe that P cannot be equal to plus or minus 1. As if so, then we know that the only units in Z are plus or minus 1. Then the ideal generated by P would be the ideal generated by 1 or minus 1, which will be equal to the whole of the Zx, right? We have already seen this, that if I have a unit in Zx, or rather I have a unit in an ideal, then the ideal must be the whole ring. And you can observe that 1 is a unit in Zx as well, right? Right? It's in fact the unity in Zx, right? It works as a unity in Zx. Yeah. So this automatically wholly holds, and we have already analyzed the fact that the ideal generated by x and 2, this cannot be the whole of the ring Zx. So 1 or minus 1 cannot be the generator. Therefore, P must be plus or minus 2. Now suppose P is equals to plus 2, then, and the same will hold for minus 2 as well, then what is the ideal generated by 2 in Zx? It should be the polynomials of the form fx times 2 times fx, right? Such that fx is in Zx, right? That implies that the coefficient of the degree 1 term, if exists in the first degree term exists, the coefficient it must be even, right? But then that implies that x cannot be in the ideal generated by 2, because here the degree is 1, right? Therefore, we have reached a contradiction, because we need x to be inside this ideal, right? And thus, therefore, it cannot be a principal ideal. Okay? So, what we conclude is that 2x is not a principal ideal in Zx, and by our definition, that means that Zx is not a principal ideal domain. Yeah? When we will be studying factorization, different domains, we will study 3 important domains: the Euclidean domain, the principal ideal domain, and the unique factorization domain. There we will be seeing that Zx will be a unique factorization domain, and it will work as a counter example, because we will see that Euclidean domains will imply principal ideal domains, and principal ideal domains will imply unique factorization domains. But the converse won't be true. That if you have a unique factorization domain, it need not be a principal ideal domain, or if you have a principal ideal domain, it need not be a Euclidean domain. So Zx is not a principal ideal domain, but we will see that it will form a unique factorization domain. Okay, this will be something which will be seen eventually. Okay. Now what we need to do is to talk about quotient rings. Okay, fine. So let's so let's get a new page. Quotient rings. Okay, fine. Let's see. Okay. So for the quotient rings, as I had said previously, that we need to talk about ideals, and we will see when we will be proving the operations, we will see that we do indeed require ideals. Okay. Now, so let R be a ring and I be an ideal in R. Define R mod I to be the collection of elements of the form R plus I, such that R is in capital R. Okay, fine. Then define the operations as follows. Okay, so take 2 elements from R mod I. This is what we call, in literal sense, it's what we call R mod I. So R plus I plus S plus I is equals to R plus S plus I, and R plus I times S plus I is equals to RS plus I. Here? Okay. Now, if you carefully analyze this, a simple way to talk about this. See this R plus I, so I can choose an element, say R plus I times S plus I, S plus J, let's say, so that I and J comes from I. The elements R plus I basically that only, right? R plus I is basically the collection of the elements of the form R plus I, where I comes from the ideal capital. So what does this gives us? This gives us that, so it will multiply this Rs plus Is plus Jr plus Ij, right? So this is an element of I. So therefore, for this to be equal to Rs plus some element of I need these two to be also elements of I. And in that case, I will require elements of the form Is to be elements of I. Now, S was coming from R, right? So we require the notion of an ideal in order to define these operations. Getting my point? Right. Okay. So once we have this, now 0 plus I is simply I, and 1 plus I is as it is. So this works as the identity of R mod I, and this works as the 0 of R mod I. So this makes R mod I as a ring. Moreover, this map pi from R to R mod I by sending an element R to R plus I is called the natural map. And you can observe that this is actually a surjective map. Okay, this is a natural surjective map. Because any element to choose from here is of the form x plus I, then x will be mapped to this element. Right? Clear? Fine. No, we just said that this is a ring. So for it to be a ring, we need to check that whether the operations are well defined or not. Okay, that's quite an easy check. So we need to check that the operations. This is the last part we are doing in this lecture. The operations on R mod I are well defined. Okay, let's see. So choose R plus I equals to R prime plus I, and choose S plus I to be equals to S prime plus I. Okay. What do I need to prove? I need to, okay, I am, okay, let's see. Okay. So we need to prove that the addition holds in both the cases. See, R plus I. So what does this imply? This implies that R minus R prime is in I. Okay, this is from the definition. This implies S minus S prime is in I. Right? Now this implies that R plus I plus S plus I is equals to R plus S plus I. Now if R minus R prime is in I, so I can write R as R prime plus some I. Here I can write it as S equal to S prime plus some J. Both I and J come from I. So this can be written as R prime plus I plus S prime plus J plus I. By commutativity of addition, this is R prime plus S prime plus I plus J plus I. But since I and J are already in I, this is R prime plus S prime plus I, which is R prime plus I, S prime plus I. And in the same way, you can check the well-definedness of multiplication. Right? Okay. So let this lecture be up to this much. In the next lecture, we will talk about the isomorphism theorems which we have in case of rings, which will be extremely relatable to the isomorphism theorems in groups. Okay. So meet you guys in the next lecture.